Okay, welcome back everyone. So we have our first junior speaker, Dominik Burek, who's going to tell us about higher dimensional Calabi-Yau varieties of Kummer type. Please.
Thank you. Hello, good morning everyone. First of all, thank you organizers for the opportunity to talk about my results from PhD thesis. My research concentrates on Calabi-Yau manifold, which is for me a complex, smooth, projective manifold satisfying two conditions. First of all, I would like to have trivial canonical divisor. And second assumption is that if cohomology groups vanished for positive I smaller than dimension. Here, D is the dimension. Equivalently, we can say that there exists a no vanishing holomorphic D form on X, and there are no global holomorphic I forms on X. So one of the most popular way of constructing new Calabi-Yau manifolds, especially which are non-complete intersection and non-toric one, is a quotient of some kind of Calabi-Yau type variety by a finite group acting on it. Calabi-Yau type, I mean with trivial canonical divisor. But well, if we do such a quotient, then always in points corresponding to non-trivial stabilizers, we will get a singular point. So we need to have a good resolution of singularities. And we say that as a resolution of singularity is discrepant, even only if it does not change a canonical divisor. So if we start with a trivial canonical divisor, then after the discrepant resolution, we will get also a trivial canonical divisor. So everything is satisfying. The term discrepant means that there is no prefix dis in discrepancy, so no discrepancy in the canonical class. And well, if we look at the finite subgroup of SL2, then the surface C2 over G admits a unique discrepant resolution of singularities, and they are commonly known as AD singularities or also Duval singularities. So this is the history in dimension 2 and all the results of Klein. And in dimension 3, the situation is much more difficult, but still we have a discrepant resolution of singularities when we divide C3 by a finite subgroup of SL3. This discrepant resolution is not unique here. They are connected by the process, by the flop process. But well, most important information that we have a discrepant resolution. In higher dimensions, the situation is bad, even if we take such a nice looking and easy looking quotient, C4 over the subgroup generated by identity and minus identity matrix. Such a variety does not admit any discrepant resolution, and it's in fact not so easy to prove. So we expect in higher dimension, the situation is very difficult. For me, I focus on higher arbitrary dimensional Calabi-Yau manifolds, especially the construction given by Zink and Hulek. This construction involves elliptic curve ED with an automorphism of order D, where D is equal to 2, 3, or 4. Then we can form the following group, which is in fact isomorphic to the n-1 copies of cyclic group of order D. And this group acts on the product, which is in fact Calabi-Yau type variety, because this is a product of elliptic curves, by a phi d to the mi on the I factor. Phi d, it's just this automorphism of order D. Then the authors prove that there exists a discrepant resolution of singularities of that quotient, and consequently they obtain an arbitrary dimensional Calabi-Yau manifolds. It turns out that this manifolds has many nice arithmetic features. For example, they are modular in some sense, and also very interesting psychotheoretical situation. Well, since the order of an elliptic curve divides 24, we see that here one case is missing, exactly 6. All right, and in fact, the argument given by authors cannot be adopted in this situation because at some point they obtained a singular point which cannot be resolved in crepant way. So my first question, my first result from PhD is to complete this theorem to this missing case equal to 6, and I will sketch the proof how we can do this. So to conclude it, I need a statement which is true for arbitrary 2 Calabi-Yau manifolds. So take Calabi-Yau manifolds with automorphisms of order 6 such that they are purely non-symplectic. I mean, they act on the period as a multiplication by the fixed 6th root of unity. Here omega xi is a chosen generator, the period of my Calabi-Yau. And well, I need to have several conditions on fixed loci of both eta 1 and eta 2, both automorphisms. First of all, I would like to have smooth divisors in the fixed point locus of eta 1. In particular, it means that the local linearization in points in this fixed point locus of eta 1 is of the form zeta 6, 1, 1, 1. So this is the matrix with terms on diagonals equal to zeta 6 and 1, 1, 1s. So near any point we have this kind of linearization. If we have a fixed point locus of eta 2, I want to have only disjoint union of submanifolds of codimension at most 3. In particular, when we took a codimension 1 submanifolds, then the local linearization should be exactly zeta 6 to the 5. And if we have a codimension 2, that we have only 2 options. So options like this and this, and zeta 6 free and zeta 6 square, because in total we need to have 5. What else? In points which are fixed by the square, but not fixed by the automorphism itself. So this set of points is a disjoint union of smooth divisors, and in particular, we have the following linearization. So this is zeta 6 square, which is zeta 3. And similarly for third power, because it's also important to check what happened in points which are fixed by some power, but not fixed by the automorphism itself. Well, with eta 2, the same. So we need to have also smooth divisors in the codimension at most 2 in the fixed point locus of eta 2 square minus fixed point locus of eta 2. And in fact, naturally, we have only 2 options for linearization. But the 7th condition is the most important, because I told you that I would like to have only in fixed locus of eta 2, I would like to have submanifolds of codimension at most 3. So for codimension 1 and 2, we have we put all options which we can. So we have all type linearizations. But in the third codimension, I would like to have only local linearization of that form, because, for example, I exclude here 113. Okay, 113 is not good for me, but I only want 221. Okay, and under this assumption, it turns out that the following proposition holds. So if we take a product of my 2 Calabi-Yau varieties and and the quotient of this product by a group of order 6 generated by a product of 2 automorphisms, then in fact this quotient admits a resolution of singularities, and moreover, and this is the most important part, identity times eta 2 induces Z6 action on the resulting crepant resolution. So thanks to this, I can continue inductively my approach, because well, this variety has the same has automorphism of order 6, which has the same properties as the automorphism of X2. So we can continue whole process. And now I would like to give you a sketch of the proof. So for this, I used approach of toric geometry. Well, easy to see that if we consider the automorphism, which is the product of both automorphisms, then the local linearization around any fixed points has the following types. This symbol means that locally it's just a singularity coming from xy when we maps xy to zeta 6 times x, zeta 6 5 times y. All right. So of course here we have a lot of ones, but locally analytically it's just isomorphic. Okay, this type of singularity with that type. What kind of singularities we also obtained? 1, 1, 4, 1, 2, 3, and well, from codimension 3, I put 1, 1, 2, 2. Well, I told you that in dimension 2 and 3, we have no problems with existence of the Crepon resolutions. And in fact, in fourth dimension, it is also not difficult to construct the Crepon resolution of that singularity. But the most difficult part is to check that the second sentence of this proposition holds. I mean, we can extend this action. The action induces an automorphism and has the same properties as we put on X2. So we need to find a method to see how the action, what kind of action is induced by on the resolution of singularity of that type singularity. And well, in dimension 2, there is a nice paper given by Reed. And it's also, I think it's just the introduction to toric geometry. When we have local singularity of the type 1,5, then using well the composition of the segment, which can be called one junior segment, which is nothing else as just a quadrant in R2, positive quadrant in R2. We can find the decomposition of these segments into 6 parts, and these parts corresponds to affine charts, affine parts of this map from x1 times x2 to the resolution. And we can check how the maps look like. And in fact, having these maps, explicit description of these maps, we can check that the action of identity eta 2 has linearization, of course, this kind, and it lifts us to the resolution as the following. So everything agrees with my assumptions, because here we have 2, 3, 2, 3, 1, 4, and one codimension, so it's fine. In third dimension, when we have 1, 1, 4, the situation is much more difficult, but there is a paper, beautiful paper of Crow and Reed, how to calculate A-Hilp C3, which gives an algorithm, the method, how we can deal with such a kind of resolution of singularities of that type. Well, in fact, all such resolutions corresponds to the subdivisions of the junior 3 simplex, which is nothing else as just positive quadrant in R3. So practically, we need to divide our junior simplex, and the slice of it is just an equilateral triangle, into 6 equal volume, equal area parts, like here, all right? Because here, the points which are here are the junior points, I mean, points with barycentric coordinates sum to 1 in this junior simplex. So we need to find a subdivision in vertices at junior points. What else? They give also a method how to read nicely from that picture maps from x1 times x1 to the resolution. And here I put also arrows, because any side, any edge, and a side of a triangle is a side of 2 triangles. So I would like to read these maps using some orientation, by fixing some orientation. And well, the edge, for example, xy will be used for this triangle and this triangle. And in one triangle, this will be just xy, but in this triangle, one of the coordinates will be just y over x. So everything should be grew nicely thanks to this. And well, we can check how the maps look like and check that the action leads to the resolution as expected. Well, in 1 to 3, the difficulties came, and this is, for example, one of the reasons why Singh-Hulek argument does not work, because here we have exactly 5 subdivisions. Okay, in the previous example we have only 1 subdivisions, but here we have 5, but only 1 corresponds to lift, but only in 1 decomposition the action leads to the resolution as expected. In the rest of the pictures, if you take a gray triangles, that they corresponding maps leads to the bad linearization. So when we do the same analysis for that decomposition, we see that that this leads as expected. And in 1-1-2-2 example, so here we can transform the question into subdividing tetrahedron in some 6 small tetrahedron with equal volume. And here are junior points inside this 4 junior simplex, and I hope I displayed nicely how we can divide this tetrahedron into 6 equal volume parts. And in the final step, we need to also take care of that points, but it's not so difficult because first we divide by Z2 and after that we take Z3 action and vice versa. So everything is okay now. All right, by some trivial induction argument, we can just complete the theorem given by Singh and Hulek. And in fact, if we take a product of elliptic curves with automorphism of order 6 and we divide by a group, then we have a crepant resolution of singularities. Okay, in the next part, I focused on some generalization of that construction. So one of the most important construction of Calabi-Yau threefold coming from mirror symmetry. The first example which is symmetric with respect to this mirror symmetry is the Borchardt-Voisin construction, which admits a K-free surface with involution, non-symplectic involution, and the elliptic curve also with involution. Cataneo Garbaniati, their paper in 2016, generalized this theorem to allowing SD purely non-symplectic automorphisms of order not necessarily 2. So not only involution case like in Borchardt and Voisin, but also 3, 4, and 6. And they also took a elliptic curve which admits automorphisms of order D as on the previous slides. And they showed that the resulting quotient has a crepant resolution of singularities, which is a Calabi-Yau threefold. I would like to extend this this construction because the proposition proven on the two slides ago allows me to construct the crepant resolution of that quotient. So I can take a K-free surface with automorphism of order 6 and arbitrarily many elliptic curves with automorphism of order D. I can take exactly the same group as in that Singh-Hulek construction, which also preserves canonical bundles. So this is a Calabi-Yau type variety, and we divide it by a group. So using this proposition, we can prove that there exists a crepant resolution of it, and the resulting variety, which I called YDN, is n plus 1-dimensional Calabi-Yau variety. So the next step for me is a computation of the Hodge numbers of all resulting variety which I constructed. So for this, I used a Chen-Ruan cohomology, which is defined as follows. So this is the direct sum over conjugacy classes. And here is also direct sum, and U is just a connected component of the fixed point locus of G. Here we consider a G action, and H is just the H of the matrix linearized. So the definition of H will be on the next slide. But here the most important fact is that on this direct product, we act by centralizer. So this complicates this formula a little. This cohomology for arbitrary orbifold, but here we have a quotient. This cohomology was introduced in 2004. What is more important? Here the H is just the, if we take any matrix of finite order, then if we list off all of the eigenvalues, then for some eigenvalues can be written as this for some rational numbers, and the sum of these rational numbers is H. So for example, when we have a singularity 1, 6, 1, 5, then 1 plus 5 over 6 is 1, so this is H1 point. The most important theorem is the theorem given by Yasuda. If we have a Crepant resolution of singularities of the quotient X over G, then we can compute the Hodge numbers as a orbifold Hodge numbers of the quotient X over G. So the main advantage of this formula is that we don't need an explicit construction of a Crepant resolution. We only need the existence of the Crepant resolution, and we can apply this formula to compute all Hodge numbers. So how we can describe, how we can calculate these Hodge numbers in some nice way? Well, I took a generalization of the construction which I gave on the previous slides. So I took arbitrary Calabi-Yau of varieties which admits automorphisms, non-symplectic automorphisms of order D. The group G is absolutely the same as previously. The action is the same, and we can form the following quotient. Okay, so I assume now that this quotient has a Crepant resolution of singularities. Thanks to this, I can compute the Hodge numbers using Yasuda results. And for this, I defined the following. It's the Poincare polynomial in two variables of the cohomology. And here I take the well, here's the fixed point locus of K power of the automorphisms phi ID, and here I take zeta di part in the ZD action. Okay, so this is eigenvalue part, and well, so this is a Poincare polynomial, so this is some polynomial, and I proved that if we assume that the fixed point locus is a divisor, then we can compute Hodge numbers of this variety using the following formula. In fact, I don't need this assumption. To avoid this assumption, I need some kind of correction, but for this presentation, I took only example for which fixed point locus is a divisor, and also another example for which we need some kind of correction. But with a correction, the same formula holds. To prove this formula, we need to analyze how the action, what is the action on the cohomology groups and Chen-Ruan cohomology. Well, so it is enough to form the following tables, write all polynomials, Poincare polynomials, then to fix some column, then to compute the scalar product of the vector, which is marked as gray, with the following vector, and then multiply all values for all tables. Okay, so I would like to present it nicely. So suppose that we have an elliptic curve which admits an automorphism of order 6. So the corresponding table has the following form. We can compute that it has the following form. This is easy because here the computations are put only on the fixed point locus. For example, for elliptic curves, just a points. All right, and then we can compute manually that HPQ, Hodge diamond, Hodge numbers can be written as the following coefficients of this Puiseux polynomial, because this polynomial has a non-rational exponent. So we can, it's enough to just take x coefficients in xp to the times yq of that polynomial to conclude what is the HPQ. And well, we can formulate the following theorem. If we consider manifolds xdn, so Singhuleg manifolds for d equal 2, 3, 4, and 6, then the Hodge numbers may be represented as the following coefficients of the polynomials. All right, and some Hodge diamonds. We see that the Hodge diamonds has very simple structure, so only non-zero terms are on vertices and on the main diagonal. Well, here's the example with a correction, because if we have a K-free surface with automorphism of order 3, that there is a point there with linearization zeta 3 square, and this point has H2, so we need a correction here. All right, and using this correction, we can fill the table. So for elliptic curves, nothing changes, but here we have a correction, and this correction is only this xy. Okay, so if this example will not have fixed points with h which is greater than 1, then probably this xy shouldn't be there. But using this correction, the correct table is the following. And here also manually we can check that we can compute Hodge numbers in terms of as a coefficient of this huge, in fact, polynomial. This is example d equals 3. In d equals 6, the situation and the formulas are much more difficult. And some examples of Hodge numbers. Of course, we see that the structure of the Hodge number is much more difficult. This is thanks to the K-free surface, which we put in the construction. All right, and the last thing, zeta function. Well, here the situation is much more difficult because, well, zeta function is of arithmetic nature, so it depends on the member of family and the prime power. But still, we can find a method how we can compute zeta functions of such varieties. So the context, the setup is absolutely the same. We consider the following product of Calabi-Yau type varieties, and we divide it by the action of some power of the group ZD. Also, we need automorphism, non-symplectic automorphism of order D. And then using some paper, the Frobenius action on the Chern-Yuan cohomology by Rosen, by defining the following things, which is also some kind of rational function in 2 variables. And here the action on the cohomology of some power of this automorphism also is easy to compute. We can infer the following theorem. And again, we don't need this assumption, okay? Using this assumption, the proof is easier, but to have a general situation, we need also some kind of correction. So the following formula holds, and well, maybe I will present it how we can use it. So for any variety xi, it's enough to form the following tables with zi's, then took some column, and then also we need to here evaluate this vector on this vector. So we took just zxioj on t on this, on the third term, and so on. Then we can take the tensor product of all results. Here the tensor product is a unique extension of the usual tensor product. So here I need the tensor product for rational functions. And finally, it's enough to multiply all tables and just take -1 to n+1 power of the results. And here is some kind of example. So S6 is an elliptic curve with this kind of Weierstrass equation. In fact, this is a elliptic fibration with 1 type 4 fiber and 2 star fibers. And for this S6, let E6 be the elliptic curve with automorphism of order 6. So we can fill the table for elliptic curve in such a way. For the K-free surface also in such a way. Here is the correction. 18, this K-free surface, it turns out that it has 15 points, P with linearization zeta 6, 3, 4, and 2, 5. So together 15 points with that kind of linearization. And also we can manually compute the zeta function of the resulting manifold. Well, but this computation was really difficult using by hand, but fortunately, this is the corresponding Hodge diamond, but fortunately, all methods can be implemented in many programs, like for example, MAPE. And here are the results for the for this quotient. And if we take n equal to 4, also for n greater or equal to 4, unfortunately, formulas are too long, but they can be easily computed using MAPE. And the corresponding Hodge diamond looks like the following. So as we can see from the powers, from the exponents of denominators, we can of zeta function, we can also check what is the Hodge diamond. So this is some kind of agreement that the computations coincide. And well, that's all. Thank you very much. And thank you.